All right, welcome back. This is lab number 9 for Math 155. Today we're going to be talking a little bit about velocity, speed, and position and acceleration. We'll be talking a little bit about some related rates, and we will again see some implicit differentiation that we saw last week. Without further ado, we'll just get started with the problem. So the first problem we have the position of a particle on a line is given by s of t equals t to the fifth minus 6t cubed minus 6t plus 250, where t is measured in seconds and s is measured in feet. Now what I want you to do here is find the velocity of the particle at the end of 6 seconds, find the acceleration of the particle at the end of 2 seconds, and finally, what is the position of the particle after 14 seconds. So the first thing that I will do is to define, I will actually define S. So S of t is given by, and make sure that you're in math mode. So S of t is given by the following as t goes. So remember the t goes to, this is going to be important because we're going to be passing values into the function. So we want to make sure that we tell Maple that we are going to be passing these values. So we have t to the fifth minus 6t cubed minus 60 plus 250. So let's make sure that's right. So t to the fifth minus 6t cubed minus 6t plus 250. So that is correct. So now this right here is the position of the particle. Now we have to find the velocity of this particle and the acceleration. If you remember from your lecture, the velocity for the particle is given by the first derivative of the of the um, of the function. So we have that diff of the function, and the function is s of t with respect to t. Actually, let's do just s. Remember that the velocity of the particle is going to be given by the first derivative, and the acceleration is given by the second derivative. So let's find the first derivative of um, of s, and make sure that you define this correctly. So we have s of t in terms of t, that's going to be equal to 5t to the 4 minus 18t squared minus 6. So that is the first derivative of t. Now I'm going to call this the velocity. So the velocity, and make sure that you are again in math mode, velocity of s is given by, as t goes to the following, it's given by 5t to the 4 minus 18t squared minus 6. So that is the velocity of s. So at the end of 6 seconds, the velocity of, once again make sure you're in math mode, at the end of 6 seconds we simply just pass in 6 into our function for velocity. So at the end of 6 seconds we see that we are traveling at 5,826 feet a second. Now we could find the acceleration of the particle by simply taking the second derivative of the function s. Well, since we already found what the first derivative is, we simply take the derivative again of the first derivative. So the first derivative we call velocity of s. So we're going to take that derivative in terms of t. And we get 20t cubed minus 36t. And this will be the acceleration of, of the particle after t seconds. Now, what will be the acceleration of the particle at the end of 2 seconds? Well, let's call this acceleration of s, and that is going to be the following function, which we have already there. It's t cubed minus 36t. And now we simply do acceleration of s after 2 seconds, and that's going to be 88. So this particle is increasing at a rate of 88 feet a second. The speed is increasing at 88 feet a second. Now, probably the easiest part of the problem, I left it for last, is what is the position of the particle after 14 seconds? Well, that is simply just this function evaluated after 14 seconds, because that's the position of the particle itself. So if you wanted to find out where the particle is after 14 seconds, then we just simply do s of 14, since that's what we called it up here, and we get that we are at 521,526 feet, which is quite quickly. This particle is moving very fast. So that is the end of this particular problem. Just remember that the first function you're given is always, unless otherwise told, of course, unless you're otherwise told this, is going to be the position. The first derivative is the velocity. The second derivative is the acceleration. You could have, and this is something that you could see on your final exam, you could be given the acceleration and then asked to find the velocity and then the position. And this we will see coming up in a couple of weeks when we begin to talk about the antiderivative. Okay. Okay, for this problem, for problem number 2, we have that air is being pumped into a spherical balloon such that its radius increases at a rate of 0.25 inches a minute. And we are asked to find the rate of change of its volume when the radius is 13 inches. Here we have to know a little bit of middle school algebra. And one of the things that we need to know is that the volume of a sphere is given by the following formula. It's given by I'll call it capital B, volume, and I'll say such that T, and I'll explain why I'm doing this in a second, goes to 4 over 3 pi times r cubed. So this is the formula for the volume of a sphere, 4 over 3 times pi times r over cubed. Notice that for pi, instead of using the symbol, I could have used the symbol for pi. You could just go and scroll down and you'll be able to find it. But instead of using the symbol for pi, what I did was I just wrote capital P and then I, and this will give you pi. Now, when we talk about related rates, when we take the derivative of this particular function, we do so implicitly. So when I take the derivative of this, what I will have is I will have for v, instead of just having 1, I will actually have dv dt. So that's how I'm going to write it, dv dt. And the same thing for r. So for every variable, pi here is a number, not a variable. So for every variable that you see, you will have the derivative of the variable times the variable dt. So for r cubed, you will have 3r squared times dr dt. And then the dr dt actually corresponds to the rate of change of the radius. And we have that information. Similarly, if you were given something with length and width, like the area of a square, then when you take the derivative of the area of the square, then you will have, let's say the length is x and the width is y, then you'll have dx dt times dy plus dy dt because of the chain rule, because of the product rule. And obviously you'll have the x's and the y's around there. But now here what I have is that we know that the dt is going to be equal to 0.25 inches. That is information that I'm given. We know what the radius is. We know that r is going to be 13. That is given. The question is, what are we finding? We are finding the rate of change of the volume, which is really dv dt. So this is what we are finding, the rate of change of the volume. So the new equation will be the following. Is dv dt equals, like we were saying, 4 divided by 3 times pi, and then the derivative of r cubed, which is 3r squared, times dr dt. So this was going to be, this is what our new equation is going to be. Let's make that bold. So let's solve it. Since we now have all the parameters, we know what the RDT is. The RDT is going to be the value that we're given. We know what R is. We're also given R. So the only thing that we're missing is dv dt, which is the derivative of v. Everything else is a constant. 4 over 3 is a constant. Pi is a constant. So we could use here an eval to evaluate this. So we could do eval. So we have 4 over 3 times pi times 3 r squared times dr dt when r is 5. Hold on, I put this as the exponent, times dr dt. And we know what dr dt is. I could just put it in there. I actually don't have to write it. So dr dt we have is 0.25. And we have that r, which I could just put in there. R is going to be 13. So we have 13 squared times 0.25. Well, I'm using an eval, so let me keep it as r squared. And this is when r equals 13. So I'm using an eval, so I don't need to plug in. And when we have that, the value for dv dt, meaning the rate of change of the volume, is 530 inches per minute. So the rate of change of the volume, make sure you are in math mode, in text mode, not in math mode. So the rate of change of the volume is 530.93 roughly inches per minute. And that is it for this problem. The most difficult part about this type of problems is knowing what formula or equation is at work. So you could have something that's given by, instead of being a sphere, it could have been like a rectangle or a triangle, or some other type of geometrical shape. And if you know what the volume or the area is, then you'll be able to take the derivative implicitly and then make the substitution accordingly. And hopefully you're given enough information to solve this. If you're only given one piece of information, then it becomes more challenging to solve this type of problems. So if I only were to give you the rate of change for R, and I don't give you R and V, then at least for the level that you are in this class, you will probably not be able to solve this and get an actual numerical solution. All right, for problem number 3, we are asked to, for the function f of x equals cosine of x minus sine of x on the interval negative pi over 2 to pi, to determine all the intervals where f is increasing or decreasing. And we could do this by simply taking the derivative, finding the critical points, and to find the critical points, we need to find the critical values. And we find those by setting the derivative equal to 0. So let's first define the function f. So f is a function that takes inputs of x, and the rule is that it performs cosine of x minus sine of x. So we have defined the function f. Now what we need to do is take the derivative of this. So to take the derivative, why am I on the left side? To take the derivative, what we will do is we'll use the diff command. So diff of f of x for x. So remember, the diff command takes the derivative of the function for the specified variable. So we have, and without a capital D, by the way. So make sure that you don't use a capital D. So it's f of x of x. So diff f of x of x. So we have that the derivative of f is given by negative sine of x minus cosine of x. Now, to find out where the derivative is equal to 0, we simply do a solve command. So we're going to do negative sine of x minus cosine of x equals 0. We are solving for x here. So we do negative sine of x minus cosine of x equal to 0, comma x. And we have that one of those points where the derivative equals 0 is negative pi over 4. Now, keep in mind that this is a graph of sine and cosine, so this is going up and down. So of course the x-axis at various points. In fact, an infinite amount of points on the axis, on the x-axis. So just keep that in mind. So now what we'll do is we're gonna plot f. So let's plot the function f. So as I mentioned before, the function is crossing the x-axis at all of these points here, and it keeps on going. Now we're interested in plotting this between x equals negative pi over 2 to pi. So here we could clearly see that is crossing the x-axis at precisely pi over 4. For the derivative, though, we have that the critical value, which is where the maximum or the minimum happens, it happens at negative pi over 4. So here we have a local maximum at negative pi over 4. So we could see that by the intermediate value theorem that we have that from negative pi over 2 to negative pi over 4, so let's write this down, from negative pi over 2 to negative pi over 4, the function f is increasing. Then, on the interval from negative pi over 4 to 3 pi over 4, the function is decreasing. And then from 3 pi over 4 to pi, the function is increasing again. Now, if you use interval notation, just keep in mind that these values will have where the negative pi over 4 is, and the 3 pi over 4 will have open parentheses, as they will not be included in the interval. And that is all that you have to do for this particular problem. You know, you just have to say where it's increasing or decreasing, and you actually have to point out the actual points where you are increasing and the intervals where you are increasing or decreasing. All right, for problem number 4, we have to use implicit differentiation to find an equation of the tangent line to the ellipse x squared over 4 plus y squared over 16 equals 1 at the point 1, 2, and then we have to plot the tangent lines and the ellipse on the same graph. So if you remember from last time, before we could use implicit differentiation on Maple, we have to open up that package. We have to use with and then plots to open up the package. Now that we have the package open, we could begin. So the first thing that I will do is actually plot this. So I will do implicit plot, and again, make sure that you're in math mode. So I will do implicit plot, and what I'm plotting is x squared over 4 plus y squared over 16 equals 1. And I'm going to plot this from x equals minus 5 to 5 and y equals, let's say, minus 5 to 5 to see how it looks. And scaling equals constraint. So here we have the graph of our ellipse. So now, let's solve this equation first up here. So let's solve that equation. And we will solve it for y first. So we're going to do solve this equation for y, much like we did last time. And we get that y equals 2 times the square root of negative x squared plus 4. And also y equals negative 2 times the square root of negative x squared plus 4. And I'm going to take the derivative of both of these. In fact, I'm going to take the derivative of the first one first. So I'm going to take the derivative of this piece right here with respect to x. And I get that the derivative is equal to negative 2x divided by a negative x squared plus 4. Remember that we're doing this because we want to find out what the slope of the tangent line is, since I'm asked to plot the tangent lines on the eclipse. So I need to find out what the slope of the tangent line is at the point 1, 2. So let's see. Let's do an eval command. So let's do eval, and we'll look at the derivative. And I could just look at this as well. It doesn't really matter. I could just put this in there. But you could have also done eval then diff. So you could do a nested, and then you could do x equals 1, which is where we want to find the slope. I'm missing a parenthesis here. I'm missing another thing. I'm missing the x here. There we go. So we have that the slope of the first line is going to be negative 2 times square root of 3 divided by 3. So we have that line 1, let's call it line 1, it's going to be equal to y equals mx plus b. Right? So that's what line 1 is. And what we have here is that we're going to evaluate what the value of the original function is at the point 1. So we'll take this and we will evaluate what the value of y is when x equals 1. So we could substitute for x and y and solve for b. So let's do this. So we have, let's do a solve and then eval. So we're going to evaluate this when x equals 1, and then we're solving this whole thing for y. So what I'm doing here, I'm plugging in 1 into this, and then I'm going to be solving for the y. So let's see what we get. So I get that y is 2 times the cube root of 3 and minus 2 times the cube root of 3. So now what do we have? Well, I could solve this line 1, for b now. So I could do solve eval, and I call this line 1. And now this is something neat about the eval command. I could pass in values by using these curly brackets for the slope, for the y, and for the x. So I could do the following. I could say m, which is the slope, is going to be equal to the value that we have here for the slope, which is this. So let's put that in there, comma. And now I have the y, which I have 2 values for y. I'm going to pick the negative value for the y for this one. I'm lying. I'm going to pick the positive value for the y for this one. So y equals 2 times cube the square root of 3. And finally, x equals 1. We know that x equals 1. And remember that this is for the eval part. So this is the eval part. We still have the solve part. So for the solve part, we're solving for b, because that will be the remaining value, because we have y equals mx plus b here. Okay. So So we get that b is going to be equal to 8 times the cube root of 3 over 3. So now we have that the tangent line equals, well, what was the slope? The slope was this value up here, right, times x plus b. And b is this value right here. So we have the first tangent line here. And now we repeat the same process with the other numbers that we had. So I'm going to do the same solve that I have up here, but I'm going to substitute the values of the y with the second y, because I only have one slope. So I'm going to substitute. I'm going to keep the slope the same. The other value for y was just negative, so I'm just going to make it negative. And x stays the same as well. And I get negative 4 over 3. So now I have that the second tangent line, let's call that tangent line 2, is equal to the slope, which is this, times x. And in this case, instead of plus, we have a minus. And we are almost done. Now we just have to plot everything together. So now I have the equation of the tangent line for both of these. So now we simply will do implicit plot. And we'll plot everything together. So to plot more than one, you have to use the square brackets. So the only one that I didn't name, I think, was the first one. So let's plot this, comma, then the tangent line 1, which was this. So remember, y equals this. I could just do y equals, that would be fine. So we have y equals this, comma, y equals this. And we'll be plotting this once more from x equals minus 5 to 5, y equals minus 5 to 5, and again scaling equals constraint. And here we have a slight problem with our second tangent line. And why is that? Let's see, where did we make a mistake? The slopes are correct, so it's the y-intercept that has an issue. Actually, let's make this negative. There we go. That's what we're missing. We're missing a negative 1 here. So it should have been 8 over this, not 4. Which makes sense, because it should look almost identical except for the sign. So now we have the correct picture. So just be careful when finding the b, especially when you're doing nested commands here. So it could be very tricky. And this is it. Notice that we have a very nice picture. These two lines are parallel to one another, and they both touch the sphere. One of them does it at the point 1, and that point we found up here. One and 2 times square root of 3, and the other one does it at -1 and minus 2 times square root of 3. So you just be careful when doing this. But your picture should look something like this when you do your problem. All right, now for problem number 5, we have that a car is traveling north towards an intersection at a rate of not 800 but 80 miles per hour, while a truck is traveling at a rate of 70 miles per hour, not 100. And we are asked to find the rate of change of the distance between the car and the truck when the car is 6 miles south of the intersection and the other vehicle is 8 miles east of the intersection. All right, so the equation that we'll be using here will be the equation of a triangle, because if you could draw this, what you have is that you have a vehicle that's traveling south of an intersection, so that's going down vertically. The other vehicle is going east and away. Is going away from the intersection, east. So that will form a triangle when you think about it. Now, we will be using the equation of the Pythagorean theorem. So we'll be using, so let me write it. So the equation we will be using is a squared plus b squared equals c squared. These problems are not too easy to see, but this corresponds to a 6, 8, and 10 triangle. So the first thing that we will do is to take the derivative of this particular function. So we're going to take the derivative, I'll call it capital D. Remember that we have two ways of taking the derivative, diff and capital D. So I'm going to take it with D so you can see what happens when we do it implicitly. So it's going to be a squared plus b squared equal to c squared. And we have that the derivative of that equals 2 times the derivative of a times a plus 2 times the derivative of b times b equals 2 times the derivative of c times c. Now here the dA is going to be corresponding to our dA dt. dB is going to be our dB dt, and this is going to be our dC dt, meaning our rates. So we are trying to find the rate of change of the distance between the car and the truck when the car is 6 miles south and the other one is 8 miles north. So what we have here is that, like I just mentioned, we have a triangle, a right triangle. So our sides are a equals 6, b equals 8, and then the length of the hypotenuse, if you were to perform the Pythagorean theorem, you'll get 10. So c will be equal to 10. We know that d of a is given. D of a is going to be 80. And we also know what d of b is. D of b is 70. So all we are missing here is to find out what d of c is. That's the only thing that is missing here, d of c. We have the value for c. We know that 2's are constants. We have the value for a, b, d of a, and d of b. So all we have to do is use a solve command and substitute accordingly. So we could use solve. And what are we solving for? Well, we're solving for 2 times 60. 2 times what did I say it was? D of a. D of a we said was 80. 2 times 80 times 6 plus 2 times 70 times b. B was 8. And that we said was equal to 2 times 10, which we know. If you were to do the Pythagorean theorem, you know that will be 10, this length of side C. And then we're looking for d of a. So we have times, well, d of c, so times d of c. So we were looking for d of c. So we do comma d of c. And we have that the rate of change between the distance of the car and the truck is 104 miles per hour. So the rate of change between of the distance between the car and the truck is 104 miles per hour. And that is all that you have to do for this lab.